High performance. It needs to be fast and it needs to be lean on memory. GCC allocates lots of memory, and I'll show you some slides later that show the difference between what we're talking about and what GCC does. And lazy evaluation. DevKit, the framework I talked about, how it did precompiled headers was really interesting. It had a database of declarations, and what it would do was, if it saw a program, and it would process it, and it would look at all the function calls you made, and it would only pull out the declarations from the precompiled header that GCC needed to see. So it was interesting where its goal was to make GCC fast by just feeding it the declarations it needed to see. And we did that with lots of lazy evaluation. Non-goals. We are not going to obsolete GCC. It's here to stay. It'll be here until I'm long gone, I'm sure. It's just not pragmatic, and we respect its ubiquity. And it is a great compiler. And it just doesn't, or isn't interested in satisfying the goals we're interested in satisfying. It's as simple as that. And I also want to say that a lot of stuff has improved. The new C++ recursive descent front end that Mark Mitchell did is a wonderful piece of work. The data structures still stink, but the parser's great. The preprocessor is a wonderful piece of work. Zach and the guys did a great job on that. So it is not a total piece of crap. It is, it is a real good compiler. Okay. It again just doesn't want to satisfy the needs that we need met. So. And another non-goal is support non-C-based languages. We don't care about Java. There's plenty of people working on Java. And I don't know who's working on Ada and Fortran, but we don't care about that either. So, Apple is very centered around C-based languages at the bottom and scripting languages at the top. Right? And so you were talking about language integration. Apple has done great language integration between our scripting languages and Objective-C and C. So we do a lot of work in that area, but we don't really do much integration between the statically compiled languages, with the exception of Objective-C++. But that's done at a language level. That's not done at a runtime level. So let's look at the high-level architecture. At the bottom, we're using system and support from LLVM, the casting stuff, and all the classes listed there. We don't use much more than that. That's almost a complete list.
Well, there is a bunch of stuff. The past, I guess.
Okay, we use more.
It uses a bunch of the stuff. But
anyway, that gives you a flavor. There's a basic support library for source. This is called the Source Manager. It does source locations, ranges, buffers, file caching, and a bunch of stuff that's language neutral. So if we were to support other languages, this basic library could be reused fairly easily. The next layer up is language specific. Right now for C, we do lexing, preprocessing, and so on and so forth. The identifier hash table is very similar to what GCC has. Unique hash table of identifiers, tokens, macros, zeros. That we have a parser. So we have a hand-built recursive descent parser. Earlier I had a little rant about how we felt about compilers. For this project, we're not using a compiler, and it's worked out fine. It turns out that Chris and I feel a lot of the heavy lifting and the hard work in this framework is not in the parser. Okay, the parser. Now, I'm not saying a mere mortal is going to walk up and write a hand-built recursive descent parser. That's not the point. But we will do it. We're language people. We write it once, and it should be easy. It's to maintain. It's annotated with all the C99 spec references, and so we're happy with the way that's turning out. But by far, the preprocessor is a lot harder to get right. Chris wrote the preprocessor, and it's just a wonderful piece of work and very fast and works really well. So this DevKit inspired actions. One of the decisions I made that I was happy with in DevKit is I made an absolute separation between syntax and semantics. So the parser delegates to another object that will basically perform the semantic actions for whatever it feels like doing. And that's where it supports the multiple instances, and it supports multiple clients. So it's interesting because the parser can run, and I'll show you later, it can run without doing anything. No semantic analysis, absolutely nothing but parse. And that's really useful for performance benchmarking, and it's useful to keep that clear separation between syntax and semantics.
How can you parse C without knowing, for example, lots of time?
Say again?
How can you parse C without getting a little bit
Okay,
semantic?
the actions in its the main actions module knows how to deal with type defs minimally. So it does the minimal amount of type def analysis for C, and for C++ it will have to do some work for context-sensitive keywords, type defs. Right? So yes, but the action writer is abstracted from that. That all works without you doing any work. Okay, so at the top level, and this is one thing that DevKit did not have, I was a little bit radical in that I was so anti-data structures and objects that I said, listen, whatever you want to do with it, create your own data structures. I have no idea what you want to do with this thing, so I defer to you. That was good, but the problem is it's still, there was a high barrier of entry, right? That means you have to think a lot about the data structures. So in this framework, we're adding ASTs, which we think will be low cost and very useful, and we'll make sure that we don't include lots of silly data in them, because that's one of the design flaws of GCC is it puts too much into its data structures. They're not factored very well. And that's a fix me. We don't have an AST to LLVM generator yet, but we will. So,
Question?
yes. Oh.
So what's the philosophy here on optimizations that some people do in the front end, like constant folding or inline?
We do no constant folding. Okay. Again, we want to support source-to-source translation. So these ASTs directly model what you typed. Okay, precisely. Okay. So we will do constant folding, but we will do it on the AST. Right. It'll be a separate pass.
In contrast, GCC, as it's parsing, basically folds expressions as it goes, right? Which leads to a large class of bugs, diagnosing illegal constant expressions and stuff like that. There's a lot of problems with that.
If you're learning, I suppose, same story. No relying the front end.
So.
Okay.
So this AST is very much oriented for the language that you parse?
Absolutely.
So
Our ASTs, I'll show you the hierarchies and the objects later. You will, being a C programmer, you will recognize them, right? So here, Chris has named it Clang. It's a driver right now. Clang is not the name of this framework. The framework is not named. In fact, I hear LLVM isn't even named, which that's another story. But this is a working name.
Yes, Steve has realized that I'm not very good at naming things.
I told him he could have the name DevKit if he likes it, so we'll see. Okay, so here's a sample driver, basic stuff. We support multiple arch options. The third thing here, you can see we have a switch called parse no-op. We're giving it this big header, which I'll talk about later. All that says is install the actions module, which does nothing but, again, the slight bit of type analysis that has to be done. And so we're able to time it without doing any semantic analysis. So then when you take that switch away and we build the ASTs and we do type checking, you know exactly what the cost is. And again, I'll show you data to show you how fast this compiler is. So before we get into a bunch of numbers, let's look at diagnostics. Remember I said this was a goal of ours. So this is a silly contrived example that fit on the slide. And you can see that GCC produces two errors here, invalid type argument and invalid operands to binary. And you have to look at the code quite a bit to understand what it's really saying.